Well, good morning, afternoon, wherever it is where you are. I've been ill for a couple of weeks, so I haven't had time to do a really interesting video on this. So we'll do it the old-fashioned way with pen and paper and a bit of PowerPoint. Um, this is a kind of a complicated topic anyway, so it may be worth unpacking and going through a little bit slower anyway. So let's look at what we're going to do. We're going to do rotational vibrational spectroscopy, and if you know the clues in the name there, we're going to be doing two types of spectroscopy at once, or at least we're going to be looking at two different phenomena in the same spectrum. And so let's have a look at what we should already know. Let's recap the two big chunks of this lecture course before we then slam them together. First, there's rotation. So that is where you need to know things like reduced mass, the rotational constant, all of that kind of thing. And that helps get us bond lengths because our molecules are tumbling over each other or rotating around. And you should know that that is not a high energy process. We are not taking atoms and forcing them against an electric field. They are quite tumbling quite freely. So it's a very low energy process that only requires microwaves. And it's all governed by the quantum number J. That is the same J you see in the total angular momentum around atoms if you come across that in atomic spectroscopy. And there's also vibrational spectroscopy, so that is where the atoms actually are moving against their own electric field. So it takes quite a bit of energy to push atoms together, quite a bit of energy to pull them apart, and to get them to vibrate against that requires infrared energy. So that's all the stuff about oscillators, harmonic oscillators, anharmonic oscillators, potential wells that plot out how the energy changes as you change that bond length. Now, for more complicated molecules, that potential energy surface is a lot more complicated than just a single graph. But usually there we'll get computers to do it. We'll do that a bit in computational chemistry later. And that's all governed by the quantum number V. So once you know what J is and what V is, we can move on to combining them, seeing what happens. And so where are we going to go with this? We're going to look at a real infrared spectrum. So if you look there on the left of the screen, you can see a sample of a real infrared spectrum, and that looks very complicated. There is a lot going on in it. There's dozens upon dozens of lines visible there, and that's a bit odd because when you look at the theory underpinning spectroscopy, you usually only expect one line. In fact, kind of a line of almost infinitesimal thickness. It's going to be really tiny because you've got one locked off quantized energy state and another locked off quantized energy state, and only one gap between them, and that's the line you see on a spectrum. And there should be no reason that there should be more than one of those, or that it should vary and have a line width associated with them. But it turns out actually in reality there are a few more interactions that actually change that assumption. And one of them is what we're going to look at now. We're going to look at fine structure, and it's caused by that diagram you can see on the right. So if you could very quickly unpack that diagram and you can see what's going on, you can probably understand this topic. If not, we'll go through it a little bit more detail and what's happening. So an absorbance IR spectrum, and it's in the gas phase, has a fine structure. And we are talking only gas phase here because if you start having things interacting with each other in liquids or in solutions, everything gets a lot more squashy and a lot more complicated. There's a lot more on that will change the energy as it interacts with solvent and it moves around or tumbles around with itself. But you put everything in the gas phase, the molecule's in ideal conditions. It's not interacting with anything else really strongly, so you get a fine structure out. So what does that look like? So let's switch to a visualizer, and yeah, yes, it's in sync. Excellent. So let's draw out an infrared spectrum here. So this will be our IR, and we'll do it in wave numbers. Let's say, that's per centimeter. So this is the traditional standard way that we talk about wave infrared spectra. There'll be, so let's center one. Let's say it's going to be 1500, and over here I'll put 1400 and then 1600. So actually a quite tight region that we're looking at. What we expect to see is a single peak here that corresponds to the energy gap to raise the vibrational level from one to another. But what we actually end up seeing is something a little bit more complicated than that. What we see is, starting very close to here, we have a small peak, then another peak, then another, and these are mostly evenly spaced out. We'll get on to why they're not later. And then on the other side, peaks that keep rising up and then down. And we refer to these different areas of the spectrum by different names. So here we refer to this as a branch, and it's called a P branch. So specifically, this is at lower energy. Give the handwriting there. Now, on the opposite side of that, we have higher energy. So yeah, higher energy is on the left just because that's conventionally how infrared spectra are laid out. That's not always the case. Some presentations of spectra do swap it around, so the higher energy is on the right, which is a bit more obvious, but look at the numbers. 1400 is a lower wave number, 1600 is the higher wave number, and wave number is directly proportional to energy. It's kind of one of the reasons it's actually useful. And then IR spectroscopy goes and swaps it around. This side is called the R branch. So we've got the P branch and the R branch. Those don't, I'm not aware of them standing for anything, but you might be wondering, if you know your alphabet, that's P, Q, R. Where did Q go? Well, it's in the middle. So that peak dead in the middle there, the actual band center, is known as the Q branch. So this would be, in theory, the Q branch is just the infrared transition. So if there wasn't anything extra going on here, we'd only ever see the Q branch, and that would be it. That would be our infrared spectrum. But we've got these two wings either side of it, the two branches, the P branch and the R branch. Where are they going to come from? So this fine structure has to have a reason behind it. It hasn't just come from nowhere. And ultimately it comes from rotations. So we're going to be changing the rotations at the same time. And the structure of this then reflects that change in rotation. So why is it going to look like this? Let's get a fresh page out of the book. And there we go. So why is it going to look like this? We know that there are going to be multiple transitions, but where do they come from? So I'll just sketch out an infrared set of energy levels here. So this is one energy level. No, not put it up that high. Let's put it here. Right. And I'm going to label this V equals 0. That's the lowest vibrational energy level. And then V equals 1. Now, most of our molecules are going to be in this lower energy level. Infrared is not a huge amount of energy, but room temperature is not enough to promote a lot of molecules from this energy level to this one. So 99% of our molecules are going to be down here. And if a molecule is down here and it shoots up, that energy difference there is what we see on the spectrum. But there is more going on. There are rotational levels in here as well. So I'm going to draw those in. Now, you remember the spacing between energy levels. They do get gradually bigger and bigger in rotations. So what we have here is more energy levels. So these are all molecules that are still vibrating in V equals 0, but they're rotating in J equals 0, J equals 1, J equals 2, 1, 0, 1, 2, J equals 3, J equals 4. Oh, let's put in J equals 5. Well, those molecules, they can still access those because the energy gap between the rotational levels is actually really tiny. So we have molecules all over here. We have some here, that level, that level, that level. And that's actually governed by the Boltzmann distribution. So we've probably proportionally got more here in J equals 2, 3. Relatively few in the lower one, which is one consequence of how the statistical distribution of energy works out. Very few in much higher ones. And to scale, this diagram is not to scale. This side of the diagram should be a couple of meters in like that direction away from us. But anyway, we've got other J values at the top as well. So I'm going to build this up. We've got a J equals 0. We'll have J equals 1. J equals 2. J equals 3. A little bit higher. J equals 4. And what we could do as well to avoid some ambiguity, we can say that these values are called J with a subscript 1 to say that they belong to that vibrational energy level. And we have J equals 0 to say that they belong to that vibrational energy level. And what we've got are molecules in each, and they can have a transition up from the same J value, and they can land on the same J value again. So that's gone from J1 to J1. This one goes from J equals 2 up to J equals 2. No change. And the reason I've drawn that in green is because all of those transitions have the same energy. I mean, think about that. The energy difference between all the rotations are, at least to a first approximation, about the same. So if we've moved from exactly V equals 0 to V equals 1 with J equals 0 both times, well, that's the distance between V1 and V0 is what that transition is. Any molecule in the next vibrational level up is going from maybe a couple of wave numbers higher to a couple of wave numbers higher. Okay, so that cancels out. It's going to be the same transition. So all of those transitions that go from the same rotational quantum number and land on the same rotational quantum number have the same transition energy, and they all build up to form the Q branch. So that's the Q branch, but there are other transitions that can actually happen at this point. So if you are in the lowest rotational level, remember the selection rule for rotational spectroscopy. Delta J has got to be equal to plus or minus 1. It can only move up 1 unit at a time. So if you're on the lowest level, you could actually jump up. So let's start down here, the lowest level, and jump all the way up. So we're actually going to pass where we started and land on J equals 1. That's actually a higher transition. That requires more energy. So that's going to be at a higher wave number. This individual molecule here is going to absorb at a slightly different one to any of these molecules. Now, let's have a look at this one. If we start in J equals 1, this is the one that's rotating at a little bit of a higher energy level than the ground state. That's going to absorb light. It's going to go all the way up here, past where it started, and land on the next one up. And what about here? This one, J equals 2, shoot all the way up and land on J equals 3. These are increasing in energy. Delta J here is equal to plus 1. Those are higher in energy. That is the R branch. All the transitions in the R branch are at a slightly higher energy and an increasing energy. And that's because of that. So each of these is a new branch on that side of the spectrum. can't, no, we can't, if we start at v equals 0, we can't go further down than that. So we're actually going to have to start at v equals 1 here. So there's going to be molecules still rotating at v equals 1, slightly faster than j equals 0. But it's going to go down 1 now. So we're going to come up here and, oh, it lands on j equals 0. That's actually slightly less energy. Look at the line is physically shorter. You draw this out with the ruler. I'm doing a very rough sketch here. Draw this out with the ruler. You can measure that it is physically shorter. Here, j equals 1. Sorry, j equals 2. Keep up. We're going to go up and land only on j equals 1 there. That's shorter. Each of these is actually getting progressively shorter as well. So we start on 3, we'll land on 2, we start on 4, we land on 3. These lines are getting shorter and shorter. That means they require less energy. They're going to appear at a lower wave number. So delta J equals -1. We're going down 1 J level. That's the P branch. That's it. That's why we get the rotational pine structure. We are getting slight changes in energy. So actually, what I'm going to do is go back to this diagram here. So what you can see in the a more clear version is we are starting at lower energies and landing at slightly higher energies. So these lines here are much longer than these lines. And that means we have different transitions. So here we have delta J is -1, slightly lower. Delta J is +1. Now the final thing, there's something missing from that CO. There is no Q branch. And ultimately, there is no one real simple explanation for this, apart from the fact there is a selection rule. And this applies for diatomic molecules, so carbon monoxide, HCl. Most of them do not have a Q branch. There's a selection rule that makes delta J equals 0 forbidden. That's forbidden for diatomic molecules. But it's not always true. Actually, for things like ammonia, that's got a slightly different symmetry, and it does have a Q branch in it. So whether a Q branch appears or not, it's a complicated set of quantum mechanical selection rules about symmetry that we don't really need to care about right now. It appears or it doesn't appear. As far as you're concerned, we'll tell you whether it appears or not, or you'll have a look at the spectrum and it appears or not. It is a very complicated, weird overlap integral, so I would not worry about it at this stage, why the Q branch appears or not. But that's the basics idea of where this fine structure comes from. We are looking at transitions that actually change their energy depending on how the rotational state changes. If you measure them out, they get progressively shorter. And I'll leave as an exercise to you in some questions about how much do they get shorter by and what are the spacings between those.